Whenever somebody on the Wall Street Osmium subreddit has asked about osmium plating, I've always been the first to come in and say that it's really inefficient, the yields are really low, it's just not worth it. However, that was until recently, until I did some more digging and research. It all started when I dug up this expired patent that was originally submitted and granted to the Engelhard Corporation. It is a patent for a very easy to make osmium plating bath, and it gave yields that were way better than all the other osmium plating methods, and at least twice as efficient as the second best osmium plating method. However, before I show you how I made this osmium plating solution, I'm going to show you how I made the active ingredient of the second best osmium plating solution, and that is potassium hexachloroosmate. My starting material was the leftover sodium potassium osmate solution from my last video. I already extracted a lot of osmium dioxide from this, so there's limited osmium left to work with. My initial intention was to reduce the rest of this solution to osmium dioxide and then extract that. I did this by simply heating the osmate solution so that it would decompose.
Starting to darken. Putting some more. Yep.
Unfortunately, the osmium dioxide was way too finely divided, even for my centrifuge to separate out, so I decided ultimately to redissolve it with hydrochloric acid, producing a hexachloroosmate solution. Instead of trying to dissolve it all at once, I did so in small batches, so that way I could maximize the concentration of HCl. Something you'll notice immediately is the odd color of the solution. It takes on a sort of dark yellow to greenish color. As I later learned, this is due to potassium hexachloroosmate. This was the final solution that resulted, and because potassium hexachloroosmate shares the same solubility in water as the ammonium salt, little crystals began to precipitate from solution. Crystals growing inside of this hexachloroosmate solution, and there's some floating on top. I don't think I can collect them though. I think that might be potassium hexachloroosmate, if I'm being honest. Before I decided to evaporate the solution in my newly bought evaporating dish, I did manage to salvage some crystals and photograph them under the microscope. Wow. Look at that.
Okay, this is what we have so far. You can see along the edges we have some brown stuff and some black stuff. The black stuff is absolutely the potassium hexachloroosmate. You can see in the center all the black stuff, that is all potassium hexachloroosmate. The liquid is a little bit on the syrupy side, just a little bit. There does not appear to be much staining, if any, on the lid. On the inside, the same. There may be some staining, but I honestly cannot detect it. Overall, this has been going pretty well. Okay, this is what it looks like right now, just several hours later. There's no more standing liquid in there, but it's still pretty wet, so I have to continue letting it dry some more. So it's going to go back in there. And yeah, then I will start extracting what I can.
Okay, and here's our final product. You can see a lot of black speckled areas. Those are our potassium hexachloroosmate. All the brown stuff, I'd probably have to look at that under a microscope. It may not be fully dried yet, but I hope it is. Fortunately, potassium hexachloroosmate is mostly insoluble in saline solutions such as potassium chloride, so it can be washed with water to isolate it. Okay guys, that black little area, those are absolutely pure potassium hexachloroosmate crystals, all of them. I have some more in a little vial, but it's caught up in a whole lot of potassium chloride. I may need to wash it with water, and hopefully that will get the rest of it out. Here you can see the sample beautifully lit by a flashlight. Unfortunately, as I was collecting it, I got a little greedy and tried collecting the rest of the potassium hexachloroosmate in the evaporating dish, thus getting a whole bunch of potassium chloride mixed in with it. So the black stuff is potassium hexachloroosmate. The brown stuff is some contaminated potassium chloride. Now, electrodeposition of osmium is not so easy using a potassium hexachloroosmate solution. Part of this is because of how unstable hexachloroosmate solutions can be. As you know, alkali will decompose them into osmium dioxide. However, in neutral pH, they will still hydrolyze, forming osmium dioxide. To combat all of this, there is a strict set of parameters that you can see right here. I'm not going to get into all the specifics, but I will tell you that you do need some potassium chloride to generate free chlorine to help oxidize some of that osmium dioxide to the osmol chloride, which will then decompose back into hexachloroosmate. And the maximum cathode efficiency is going to be around 30%. However, Engelhard, which if you know the history about Engelhard, I don't need to explain it to you. If you don't know the history, I'm not going to explain it here. But in the early 70s, they invented a much more effective solution for electrodeposition of osmium. The cathode efficiencies for this solution reached as high as 65 to 68%. That's pretty good for osmium. Making it involves synthesizing a complex between osmium and sulfamate, the chemical formula of which your guess is as good as mine. To make this sulfamate complex, you need to start with the solution of osmium tetroxide. I prepared mine from sodium osmate. The tetroxide then needs to be converted to perosmate, so I add sodium hydroxide to the solution. The perosmate solution needs to be of considerable concentration, so I add solid sodium hydroxide to avoid diluting the solution. After a couple swirls and some visible agitation, most of the chlorine appears to be taken care of. While you're watching me mix the solution, I'd like to explain about the two different species of perosmate. One has a 2- charge and the other has a regular minus charge. The ratio of the two is determined by the pH. At a high pH of 14, the perosmate predominantly has a 2- charge. At lower alkalinity, the perosmate is predominantly of a minus charge. At reduced alkalinities, perosmate solutions usually appear yellow or orange, while higher alkalinities usually yield a reddish to brown color. Once the sodium perosmate solution is fully prepared, I then add sulfamic acid. Once the sulfamic acid is fully dissolved, I add more sodium hydroxide to raise the pH again. Once everything was fully dissolved, I put a stir bar in it and got it on the magnetic hot plate. This heating step is necessary for the osmium to complex with the sulfamate. Gradually the color begins to lighten, and the reddish-brown color of the solution slowly transforms into a straw yellow color. This is what the solution looked like immediately after heating, and overnight it settled to an even milder yellow. The final color of the solution seems to match exactly the description of the patent.